Busy? Busy these days? No, understand. Me too. Um, so what would y'all like to do? There's so much. I was telling somebody earlier to say, like, this exam's not going to be hard, except there's just so much on it. It's the entire semester. And so in that way, it's difficult just because there's so much. So what would y'all like to do? You want to do all the free response? Just with a good review. As I told you in class, that's where I would start with the free response. I downloaded it somewhere. On a different computer in here, it's kind of strange. All right, so I did change number 1 so that it's just asking for the magnitude and direction of the electric field. So those are the 2 parts of number 1. I know it kind of sucks to take those 5 parts and squeeze them down into 2, so I got rid of part E. So just make sure you can find the magnitude and the direction. And as always, I like to start with a picture. So draw the figure. Imagine that I have a positive particle right there, and then draw the electric field vectors from each of them. So I have E2 is going to be right here, and then E1 is going to be right here. And then I can draw my angle. I want to know what this angle is right here. That would be the inverse tan of 4/3. If you do that, it gives me 53 degrees. Sorry, let me fix this pen. It's not right. Don't write this down, okay? Okay, so y'all got that, how to get that angle? How I got that angle? No, okay. So I have a triangle right here. That is a 3, 4, 5 triangle. I'm going to redraw it right up here. This side is 3 meters, this side is 4 meters, and I want to know this angle right here. And so I say the the tangent of theta is equal to opposite over adjacent. That's 4 divided by 3. And so if I solve that for theta, that is the inverse tan of 4/3. That's equal to 53 degrees. Just know the 3, 4, 5 triangle. You don't have to know it, but we've used it so much, so you might know those angles. And the 53-degree angle is opposite the big side of that triangle. All right, so I'm going to get rid of those things. Oh, I can't do that here. So once I do that, I want to calculate E1 and E2. E1 is going to be KQ1 over R1 squared. That's going to be 9 times 10 to the 9th times Q1, which was 50 times 10 to the minus 9. My eraser doesn't work. 50 times 10 to the minus 9 divided by R squared. That's going to be 5 meters. That's the distance from here to here. It's a 3, 4, 5 triangle. 5, and then that's squared. And I'll probably give you numbers that are really easy. Those cancel. This is a 25, so it leaves 2 up there. So that gives me 18 newtons per coulomb. I do give you nice round numbers for this one, okay? And then for E2, I do the same thing. I have 9 times 10 to the 9th times Q. That's 32 times 10 to the minus 9 divided by R squared. What's R for that one? Can y'all see it? It's the distance from here up to here, which is the 4 meters. Are we good on that? You understand? Okay. Divided by 4 squared. So these cancel. This is 16 into 32 gives me 2. Oh, look, that's the same. So it's 18 newtons per coulomb. So what I have then, I'm going to redraw these vectors, is I have one vector that is 18 newtons per coulomb in this direction at 53 degrees. And then I have another vector that is 18 newtons per coulomb in the downward direction. My next step is to find the components of that vector that's in the second quadrant. And so I'll have 18 sine of 53 right here. That's equal to 14. And then 18 cosine of 53. That's equal to 9. So now I have these. Okay, no, it's not. 18 cosine 53 is 10. 10.8. 11. Sorry, 11 newtons per coulomb. All right, so I'm going to redraw those vectors. So I have 14 here. I have 18 here and 11 here. I encourage you to draw these pictures. They will help you to understand what's going on and keep you from making mistakes. Now I want to combine my my two vectors that are in the y direction. So that's going to be 4 in this direction and 11 in that direction. And then my resultant vector is going to be a vector in that quadrant, like that. To find the magnitude, I say the square root of 11 squared plus 4 squared. That's equal to 12 newtons per coulomb. So that's one part of the answer, and that would be one part A. I would say, what is the magnitude of that vector? And then the second part of the answer is, what is this angle right here? I do ask you to measure it from the positive x-axis. So in order to find that, you need to first find this angle. I'll call this angle phi. Phi is the inverse tan of opposite over adjacent. Opposite is going to be 4 divided by 11. I get 20 degrees. So that would be 20 degrees below the negative x-axis, or how many degrees from the positive x-axis? 200. I add 180 to it. So that would be part B for that question. Okay? That's the first problem that you'll have. There'll just be two parts. I'll ask you, what is the magnitude, what is the direction? You'll have to do some of those other things in between, like calculating the x and y components. That'll be all lumped in together. Again, sorry. Like, good? Yeah? Okay. All right, you're going to have a circuit that's like this. You should be able, if you're clever with circuits, you should be able to do it without many calculations, that you should just be able to look at it. But drawing the intermediate circuits will really help you on this. We did this a bunch back in this chapter. So I have 12 volts right here, 3 ohms, and then I have 6, 3, and 2 in parallel. 6 up top, 3, that's the 2 plus 1, and then 2 right there. And then if you do the 6, 3, and 2 in parallel, what's that equal to? That's 1, right? Isn't that 1? Did that right? So I have now 12 volts, 3 ohms, 1 ohm, 12 volts, and then the total equivalent resistor is going to be 4 ohms with 12 volts. That means, no, don't apologize to me. The top 2. That's a 6. This number right here? Yeah, that's a 6.
Oh, I see.
Yeah, it just sort of got mixed in with the line there. It does sort of look like a 2, but it's not. It's a 6. So this current right here, V over R, that's going to be 3 amps. That means I have 3 amps here, 3 amps here. That means I have 9 volts and 3 volts. Just said 3 times 3 and 3 times 1 to get the voltage. And that makes sense because 9 plus 3 is equal to 12, which is the total voltage I have. Now that I'm there, well, let's see, I can go ahead and do 9 volts here, 3 volts, 3 volts, and 3 volts, because those are all in parallel. Let's see if that answers my question. I want to know the voltage across R3. Oh, goodness. Okay, so what that's asking is asking, I know that there are 3 volts across this resistor, and so I want to know then what is the voltage across this resistor. Well, look, this is easy because 1 plus 2 is equal to 3. That means that I'm going to have 1 amp through each of those resistors. Okay, step back just a bit. So 1 plus 2, I have an equivalent of 3 ohms here with 3 volts across it. That's this 3 volts right here. 3 volts, 3 ohms. That means each resistor has 1 amp. Okay? So that means if I have 1 amp here, I also have 1 volt. And if I have 1 amp here, I have how many volts? 2 volts. V is equal to IR. So that means that I have 1 volt and 2 volts. So the answer to this one is 1 volt. And then the current through R1, well, R1 has 9 volts and 3 ohms. So that's V over R is I. 9 over 3 is 3. So it has 3 amps. Actually, I had that right there. And then the power dissipated in R2, I'm not going to ask you that. Okay? But you'll have 2 questions for this one. It'll just be the voltage or current through one of the resistors. Okay? We good on that one? You all good? Yeah?
Can we go over the rules for, like, combining circuits?
Absolutely. Can I clear this thing? Yeah. All right. So for this resistors in series and parallel, and while we're doing it, can we do capacitors too? Because capacitors are a big part of this exam too. So this is resistors, and then this is caps in series and parallel. All right, so for resistors in series, the equivalent resistance is equal to R1 plus R2. For parallel, it's the equivalent is equal to 1 over R1 plus 1 over R2, that whole thing. I'm going to open up a notebook file. I don't like the pen on this PDF annotator. That's not going to open. All right, for resistors in series, they have the same current. For resistors in parallel, they have the same voltage. For resistors in series, the loop rule is true. That is that the voltage total is equal to V1 plus V2 plus however many resistors I have in series. That's what we call the loop rule. And then for parallel, the junction rule is true. That is that I total is equal to I1 plus I2 plus however many I have. I think that's it. For capacitors in series, the equivalent capacitance is equal to 1 over C plus 1 over C. The equivalent capacitance for those in parallel is C1 plus C2. Notice they're flipped from the resistors. Capacitors in series have the same charge. Capacitors in parallel have the same voltage. These are very similar to the resistor rules. Remember, current is charge over time, so resistors in series have the same charge over time. Capacitors in series have the same charge, and then they both have the same voltage. And then for series, the loop rule is also true. V is equal to V1 plus V2 plus however many caps you have. And then for capacitors in parallel, remember we don't use this rule, but Q total is equal to Q1 plus Q2, but not really a rule that we use. So I like to list it because it looks the same as the junction rule for resistors in parallel. This rule for capacitors looks really similar in that both I and Q have to do with charge. Okay? Remember those, it's not just for this part because there are a number of questions in the multiple choice about resistors in series and parallel and capacitors in series and parallel. So, and then there's some explicit questions just about, what are the rules governing these devices in a circuit. Okay? We good? Is this familiar? I know that you probably haven't gotten deep into studying. You've probably been stressing over, what is that? Organic chemistry? No, you're not stressing over organic? Yes, okay. Let me clear this. We did all 2, right? Can I go to a 3? This one? So this is your right-hand rule. One part of it, part A, is really just using your right-hand rule to find the magnetic field. Remember, for this one, part A, I forget about this charge. I'm just worried about this wire. I let my thumb go in the direction of the current. It goes into the page on that side, out of the page on that side. So this, what is it, a proton? This proton is in a magnetic field that is into the page. On this side, it's out of the page, but where the proton is, I'm concerned about, is going into the page. So that's part of the answer. The direction is into the page. And then for part A, you need to calculate the magnetic field. If you look on your equation sheet, you'll find this one. Remember, it's the one without the N. That the N means the magnetic field for a loop of wire, and it doesn't have the pi. So just look for the equation that doesn't have the N, because I'm just looking at a single wire here. So this is 4 pi times 10 to the minus 7. That permeability constant is on your equation sheet. And then I is 3 amps divided by 2 pi times R. R is the distance. In this case, it's 0.1 meters. Pi's cancel. This cancels and leaves me there. That's 6 times 10 to the minus 7. So 6 times 10 to the minus 10 to the minus 6 Tesla. That is, I did that right, didn't I? Yeah, 6 times 10 to the minus 6 Tesla. So that's the magnetic field. The direction is into the page at the location of the proton. And then for part B, now I have a positive particle with a velocity in that direction going into a magnetic field that looks like that. I want to know first the magnitude of the force. F is equal to QVB. This is a proton, so it's 1.6 times 10 to the minus 19. V is 4 times 10 to the 5th. And B is, I found it, 6 times 10 to the minus 6. So I can solve that for the force. It's 24. Times that's 10 to the minus 1, 10 to the minus 8, 10 to the minus 20. I get 3.8 times 10 to the minus 19. I think I did that right. That's in newtons. So you just calculate the magnitude, and then the direction, you use your right-hand rule. V is to the right. The magnetic field is your middle finger. It goes into the page, and so the force is up. I recommend that you hold it close to the page, like this. V is in that direction, V is in this direction, and this is F. As you did on that exam, you can write those letters on your finger if you want. If that helps you. So what did I say that is? That's up. So that direction is up. Okay? You're going to have a few other right-hand rule questions. There aren't a whole lot of right-hand rules, maybe 3 or 4 or 5 on the exam, but they're not overwhelming, just a handful, a few. That one good? Hear this. Now number 4. So it will be a mirror, but it doesn't have to be this mirror. Like this, turned out this was a convex mirror, right? Yeah, it's a convex mirror. It could be concave. It could be convex too, but it could be concave. It could be any one of the scenarios that we had with mirrors. The reason that I know this is a convex mirror, I will be asking these same 2 questions. The reason I know it's a convex mirror is because the image is smaller and upright. That means that it's also virtual. So I have a virtual, upright, smaller image, and only convex mirrors make that type of image. So then I want to know the image distance. I know, first of all, that the magnification is 3 centimeters. Then the image is 1.5 centimeters. So 1.5 over 3, that's equal to 1/2. And it is positive 1/2 because it says that it's upright. So I have a magnification of positive 1/2. And I'm told that the center of curvature is 20. That means that the focal length is negative 10. Be careful, since I know that it's a convex mirror, I know it has a negative focal length. Then you have to solve the system of equations. So I recommend that you do it just like this. You say the magnification is equal to negative Q over P. And then 1 over F, that's 1 over negative 10, is equal to 1 over P plus 1 over Q. Like I said, I would lay it out just like this on your exam. Y'all did actually pretty well on this one on this past exam. Then I can solve this one. I'll just cross multiply. I know they didn't teach y'all this in grade school, but to cross multiply is really nifty for fractions like this. I can multiply across in that way, and so I get P is equal to negative 2Q. And once I get that, I get a value for P. I can take that and plug it in right here for P. So I get 1 over negative 10 equals 1 over, or negative 1 over 2Q. I'm just going to bring that negative up into the numerator. I'm going to go ahead and find my common denominator over here. That's going to be 2Q, so it's 2 over 2Q. Notice that's the same as 1 over Q. And then I get 1 over negative 10 equals 1 over 2Q. That means that Q is equal to negative 5. To make this denominator 10, this negative 10, this has to be negative 5. Okay? So Q is equal to negative 5. That's the image distance. And because it's negative 5, that means it's opposite the object. So that would be on the right side of the mirror. I did pretty well on this one, actually. Ironically, I gave y'all that those ray tracing on the free response. And I thought I gave you the really easy one, right? That was the easy one. But actually, students didn't do so well on that. Because I went and I thought, well, I'll just grade this one first because it'll be really easy to grade that question. And I graded it. And then it's like, oh, man. Like overall, like a number of y'all missed a little bit of that. Not the whole thing, but you missed a part of it. But then I went back and the other 3 questions were actually quite good. So. All right. That clear this? We good on the free response? That's it. No surprises. I changed the numbers, and like this circuit is different. This is oriented differently. The current's different direction. Velocity it's just going in different directions, but you work it exactly the same. All right. So this weekend, I would master this first. I do that the first thing you do because what you do there will help you on other things. Is that?
Will that be a proton or electron pump?
It could be either. So just beware. It could be either. Okay. Other particular questions from the exams? Hey, Strada.
Just really did you know that the angle that you took was like over there and not the other side?
On number 1? Okay, so there were 2 angles. Are you talking about the angle, this angle right here?
I mean, like noticing that angle and not the other way around.
When I was finding the components, you mean?
Like that angle, how did you notice it like from that position?
Oh, so I want to know the electric field right here. So everything that I do is going to be from that point. I'm going to have my axes centered on point A. And I know that there is an electric field vector up and in this direction because, well, if I imagine my positive test charge at point A right here, then I have a vector that points up and in that direction, right? Because there would be an attractive force if I had a positive test charge there. So that's also the direction of the electric field. And since I want to find the components of that vector, I have to have the angle there to the nearest x-axis. I'm not sure that's the question you're asking, though. Is that the question you're asking?
I was just wondering like why is it not like the other side?
Oh, why wouldn't you measure it here? Okay, you could. Are you calculating?
From the line.
Oh, this angle?
Yeah.
You could. It's just our sine and cosines would get swapped. So I always measure my angles from my x-axis. And when I do that, the x component is the cosine, and my y component is the sine. I don't know if you remember last year when we were doing inclined planes last semester, then we had a couple of cases where we were measuring angles from the y-axis, and we had to swap our cosines and sines. But you can if you do that. I think you're savvy enough to do that. But I always measure my angle from my x-axis. It makes life a lot easier. Yeah. Yeah, if Q1 was positive. Yeah, so remember to find the direction of the electric field, I imagine that there's a positive test charge right here. And then I ask myself, what's the direction of the force that it feels due to these charges? and it feels a force that's attractive to that charge. That means that the electric field is also in that direction. But yeah, you're right. If this was positive, it would feel a repulsive force. And so the electric field would be in that direction. Okay? Other questions about the free response? Or just in general? Are there particular questions that you want to look at on the last 4 exams or even on past exams? I'm just going to pull up exam 1. Really, any of these, there's not really any of them that I wouldn't give you on the exam. I don't have any, I'm not going to ask you this. I don't think that's true for really any of the exams. But particular ones that you want to work at? Not study that much yet, have you? Yeah, that's okay. And then it's still a little bit early. You have a few days. Anything at all? No? Sure. Yeah. So your equation sheet is pretty important there when I ask you about those things. Let's see, where's my equation sheet? See, here's all the equations for charging and discharging capacitors. Anytime that I have an equation that just has e to the minus t over rc, that function is going to look like this. It's a declining exponential function, decay function. But if I have an equation that has 1 minus e to the minus t over rc, that is a growth function. It's going up, right? So, for example, if I ask for the charge of a charging capacitor, then it would be this one. Or if it's a discharging capacitor, it would be this one. Be careful, though, because sometimes I give you others that aren't really exponential, or that are neither one. Like, for example, I might give you, what would that be? What would it look like? Like this. That would not be one. Or, what's the other one that I give? Like this. Yeah. I give you those shapes, but neither of those shapes are those. Okay? Does that answer your question? I want you to know the shape of an exponential function. Other questions? Okay. I feel okay about it? About the exam? Yeah. On exam 418? Of course.
Like our exam 4.
Uh-huh. You're not going to see that one. Can I talk about it there? So on this one, the easiest way to do this, I was just looking for the distance between two alternating bright fringes, like between any two orders. The easiest way to do it was to take the distance between the 0th and the 1st order. Okay. When you have this diffraction pattern, the dots come regularly in this case, and so that's what I was expecting to do, is take between the 0th and the 1st order. You know how to do that? Can I anybody do that? Okay. Because that comes up on other questions too, but you're not going to see this one. But there is another question, like this one, number 16, where you have to find the distance between to a particular order.
Oh, we can do 16.
Okay, yeah, because you are going to see number 16. I've made it a little simpler, where I took out one of the angles, because on number 16 you could have chosen either angle. You know that, right? Yeah, so the first angle was for m equal 1, and the second angle was for m equal 2, for those first two orders. And I wanted to know here, what was I looking for? Yeah, just the wavelength of the light. So I have d is equal to 3.3 times 10 to the minus 6 meters. M is equal to 1 for an angle equal to 12, or M is equal to 2 for an angle equal to 24.7. You could use either of those angles. Let's just choose these two. Doesn't matter which one. You get the same answer either way. So I say d sine theta, 3.3 times 10 to the minus 6 times sine of 12 is equal to m times lambda, and then I solve for lambda. I don't remember what lambda was. Do y'all know? 390? 690. Okay. 690 times 10 to the minus 9 meters. You will have that question, but not that other one. No idea if y'all did. I didn't really like it. Okay. What else? Go ahead. On exam 3, 17 and exam 3. Great way to study is just start with these exams. This one? Yeah, okay. So really just the sum of the angles in a triangle is 180. You need to know that. And then the incident is equal to the reflected angle. So I know that this angle is equal to 30 because theta I equals theta R. And because of that, this angle, which is part of this bigger 90-degree angle, that this is 60 degrees. You'll see how I got that? 60 plus 30 is 90. And now notice I have this triangle right here. I already have 110 degrees between these two angles. That means that this angle must be 70 degrees because 180 minus 110 is 70. That means that this angle must be 20 degrees, and so the reflected angle is also 20 degrees. It'll be the same, similar to that, I mean different angles and stuff, but where you have the two angles, theta I, theta R, are equal to one another, and then the angles in a triangle should add up to equal 180. What else? Go ahead, you can raise your hand. What's your? No? Yeah. 20 on exam 2. Probably you're gonna have the most difficulty with exams 1 and 2. Those were harder exams, and also they were farther away. So you might want to spend a little more time on those. All right, so if I have 4 ohm resistor connected to a 12-volt battery, I would expect 3 amps to flow through that 4 ohm resistor, right? V is I is V over R, 12 over 4 is 3. But instead, I have 2 amps that are flowing. So I want to know what is the internal resistance of the battery. See, the circuit that I have here is a power supply with actually 2 resistors. This is 12 volts, this is 4 ohms, and this is the internal resistance of the battery. Now I'm told that I have 2 amps, 2.0 amps going through this circuit, and so I want to know what is the internal resistance of that battery. Well, what is my resistance to give me 2 amps? Well, R is equal to V over I, so that's 12 over 2, or 6 ohms. So I have a total current of 6 ohms. That's why I'm just getting 2 amps. So that means that the internal resistance of my battery must be 2 ohms. There is an equation that we did, the delta V equals epsilon minus IR, but I find that it's a lot easier just to think about this one in that way. That I'm getting 2 amps, but I really should be getting 3 amps. So I have some extra resistance in the circuit that is causing that current to be lower than I would expect it to be. figure out what is that total resistance based on the voltage and the current, 6 ohms, and then the internal resistance is, that extra resistance that's in that circuit. Anything else, Phil? No? Has a what? A loop rule. Yeah. You'll certainly see that. That's exam 4, right? Or 3? That's exam 3, I think. No, it's exam 2. You're right. All right, number 15. All right, I want to know which of these equations are correct. In fact, you will see a question like this. So I want to know which equation is correct. So I just go through each one. I1 plus I2 is equal to I3. That's the incoming equals the outgoing. But notice here that my incoming includes I1, I2, and I3. So that one's not right. It should be I1 plus I2 plus I3 equals 0. Here I have 4I1. That one starts out wrong because I don't have a resistor in this branch right here that is 4 ohms. I have this 4-volt battery, but when I write this in the loop roll, there shouldn't be a current attached to it. It should just be 4. So it would be 4 minus 2I1 minus 8 would equal to 0. So if it didn't have the I1 right there, that equation would be correct. But because it does, it's not correct. That's a common way that I like to change it up. Minus 6. So since it's minus 6, I'm starting here and going in this direction. Plus 4I2. That's right so far because I'm going against the current. Plus 8. That's coming back over here. And then that's it. Comes back to where I started. So that one is correct. And then 2I1, positive 2I1. That means that I'm starting here and going in this direction because I'm going against the current. That's why it's plus 2I1. Minus 4. I'm going from the big side to the little side, so that's correct. Minus 4. Minus 4I2. That's correct because I'm going with the current. And then plus 6. That's correct. So these two are right. C and D are correct. B is the right answer on that one. And then you'll also have the follow-up question of that where I'm asking you what is the, let me say C and D are correct. What is the current in one of those through the 2 ohm resistor? So the 2 ohm resistor is I1. That is, I want to know what is I1 equal to. So to find I1, well, let's see, I need to pick the right loop. What loop am I going to use to find I1? It's either the left or the big loop. The big loop, right, because there's no resistor on this part, so I definitely want to get that one in my equation. So to write that equation, let's just start here and go in this direction. That is 8 plus 2I1 minus 4 equals to 0. 4 plus 2I1 equals 0. So I1 is equal to negative 2. I1 is negative 2. 2 amps up. So I1 is actually in that direction. So the answer was 2 amps. I didn't ask for the direction, but the answer there was B, 2 amps. You can see both of those, okay? Multi-loop circuits. I didn't put that on the free response, so I definitely wanted to use it in multiple choice. All right. If we sit here for long enough, I'll probably tell you more questions than I can, but have somebody come in at 4 to run. So.
Why did the sign change?
Why did the sign change? Right here, you mean? Why did the direction change? Yeah, because when I calculated this, it came out negative. And because it was negative, it means that this direction was labeled incorrectly. Okay? Is that it, y'all? Yeah. Really? 20 on exam 1. Okay, so remember on these, the important thing is to remember how I find my potential. V is equal to KQ over R. So to have a potential of 0, I have to have two equal but opposite charges that are also equidistant from each point. So for example, right here at point A, I do have two equal and opposite charges, like I have those two charges, but notice that their potentials don't cancel out because they're not the same distance from one another. Likewise, I mean, these two, these two also are not the same distance from one another. So that's not the right answer. Where is the potential equal to 0? Looks like B, right? These two distances are the same to those equal but opposite charges. These two distances are the same to the equal but opposite charges, and those two distances are the same. So B is the only one that has a potential equal to 0. All right. Okay. I'm going to call it there if that's okay. Are we okay with that? If you have any burning questions, I'll be around.